Alright, before we start, I'll recommend you to watch these videos first. If you're done, let's get into it. In previous video, we assumed that system of our electromagnetism is in vacuum, which means the constant of medium is mu0 and epsilon 0. Here, mu0 relate to magnetic permeability and specified to vacuum response due to magnetic field P, and so on for epsilon 0 as electric permittivity that's specified as vacuum response due to electric field E. So here, the question is, how if medium is not a vacuum? To answer this question, we split the section for this video, electric and magnetic response. In electric response, suppose we have matter system, let's say M, and then we generate electric field just like this. Here, if we zoom in to each molecule, let's say in this part, we will see that this molecule creates some kind plus pole and minus pole when E is not a zero vector. But if we turn off E, this molecule return to neutral again. So what happened here? This happened because of non-vacuum here. The system is inside the matter, that the matter itself is medium. So here we have these two conditions related to an electric field generate or not. These two conditions and the consequence relate to polarization, and this polarization relate to electric dipole. So what is electric dipole? Here, electric dipole is a fundamental thing we need to know for electricity in matter. That's because a neutral molecular level can create a dipole or two pole plus and minus just before because of electric field generate, just like these two illustrations. Here, let's say the distance between plus and minus pole here as d, which may be infinitesimally small. So here, we define dipole moment as p factor is equals to this multiplication, that d magnitude is this infinitesimal d, and the direction is from negative to positive, such that d here relate to displacement between minus to plus. At before illustration, we know that this definition only valid or only easy at least for a single dipole unit. So for continuous system, we define the polarization as P capital factor here that relate to the first derivative of electric dipole moment with respect to volume, or in EASE, this is dipole moment density factor, that this will create electric field E as response to external electric field. Here, we return to unit electric dipole just like this, with electric field generate to whole space here, that by Gauss' law for electric field, we can modify this equation as this. So the dipole here that create from response to external electric field, this can behave as raw matter or raw bound, that bound here is kind of bound to matter structure. So the other one here is free charge that responds electric field as we know as charge. So here it's related to raw free, that unbound to matter structure. Then we know that the dipole moment here create later as polarization, and this electric dipole creates some kind electric field because of polarization, that here electric field because of dipole moment repel to external electric field here. So P create some kind of additional electric field that repel to E. So here E because of polarization proportional to minus P capital factor here. So then we have rho bound is equals to this, and by mathematics we can modify the equation as this, which inside the divergence operator here we can define D capital is equals to this, that commonly known as electric displacement field, which this P capital factor relate to medium or rho bound, and the equation will become as this, or known as Gauss' law for electric displacement field, or just Gauss' law for electricity in matter. Next, for a magnetic response, first we know that nabla.P is always zero, so there is no magnetic monopole. So here we can define analog to electric dipole that we have magnetic dipole as fundamental source of magnetic field, which if we have magnet like this and the magnetic field of course, then this magnet system equivalent to this loop with current, let's say I capital here, that of course create magnetic field. Here I can define the parallel vector with respect to P as mu vector like this for both. That mu vector here is about magnetic dipole moment. Here, the energy because of pure magnet will equals to this, and the mu vector here in loop with I here relate to this, which A is area for a loop and the direction is along the face of surface that enclosed with the loop of I, and this energy has electric dipole analog as this. So here, we return to the magnet model and Ampere-Maxwell law for magnetic field like this. Here, we take pure magnetic case as E is equals to 0 vector. So the E vector in Ampere-Maxwell law here vanish. And then we define magnetization as M capital vector is equals to this differentiation to mu vector with respect to volume that analog to polarization as magnetic dipole density. If we back to the illustration of magnet here, if we generate external magnetic field like this, so the magnet here create additional magnetic field, let's say PD because of dipole. Here, the factor of PD and P external is not cancelling each other. So analog to Gauss law before, we decompose for current density as bound and free here, and the bound here related to matter structure, such bound is equals to this because mu related to additional current not cancelling the external magnetic field. So after that we get this, and by mathematics we got this curl equation. And notice that inside the curl here we can define this vector combination as H capital vector, or known as magnetic strength field, that analog to electric displacement field, which here magnetic strength has difference in many reference. So in some reference P is induced magnetic field and H vector is a magnetic field. So here I denote H vector is magnetic strength, so the magnetic field is as usual as P. That again we can denote as this. Here we have same problem in continuity, of course, because of this continuity equation is equals to 0. So here, because in the real world, magnet can create from electric and electric can create from magnet, J capital bound can be generated from polarization. So by continuity equation, we get this result that the last part here is Maxwell's correction. So the final result here is about Ampere law in matter, that for magnetic strength field. By summary, here I want to show you the comparison between vacuum case and the matter case. In vacuum we know as before, and the matter what we get as in this video, which vacuum medium relate to mu 0 and epsilon 0, but in matter, medium here relate to mu and epsilon in general. And for a little footnote, mu and epsilon in general here can create from epsilon 0 and mu 0 plus some addition by P and H factor here, that again by continuity assumption before, P and M here can depend to magnetic and electric field for both as response and the structure of the matter, that being medium. And that's how we formulate Maxwell's equation in matter and how it differs between vacuum and matter. I hope you enjoy this video. If you like this video, don't forget to share and subscribe. If you have any questions, please drop comment below. And that's it. See you later.